So for number 28, we've got a bead that slides on a curved wire starting from rest at point A. If the wire is frictionless, find the speed of the bead at point B and at point C. Now, one of the critical parts about this one is the fact that the wire is frictionless. That means there's no energy lost. At point A, the bead has gravitational potential energy, but no kinetic energy. And we can very quickly solve this then using the work energy theorem. So the initial energy in this case is purely gravitational potential energy, mgh. And so just plugging in the mass of the bead, I'm using 10 for gravity, and the initial height is 5 meters. We get that. There's no work done. There's no additional forces besides gravity acting on it. There's no friction, and so there's no work. And the final energy at point B is going to be purely kinetic. It has no gravitational potential energy because I'm going to define h equals 0 here at the ground. Why? It was just plain convenient. Solving this then just very quickly, whoops, wrong way. Initial energy is 20 joules, and reducing the other term there, you can very quickly figure out at point B, it's going to be moving at 10 meters per second. For those who are curious, yes, that literally means the kinetic energy at this point is all of it, all 20 joules, that it started out with at the beginning. So up here, if you solve it, we end up with 20 joules initially of gravitational potential, and that gets converted entirely into kinetic at the bottom. Now at point C, it has both gravitational potential and it has kinetic energy. The total of those have to equal the 20 joules it started out with, but the question is, how fast is it moving at that point? Doing the work energy theorem one more time. Initial energy, I'm going to go all the way from point A. Yes, I could have also gone from point B and realized it's 20 joules. But the final energy in this case is going to be both its kinetic energy and its gravitational potential, where the height now is 2 meters. Plugging in our numbers, we can actually now solve this. We know at this point that this is 8 joules. Which means all the rest of the energy must be in the form of the kinetic energy, all the remaining 12 joules. And if you solve it then, just solving this equation, you'll discover, whoops, you can't quite read it, went off the bottom of the screen. The final velocity should be about 7.75 meters per second when it's at the other position, given that amount of kinetic energy remaining. Notice again, the total energy remains constant. It just gets converted from one form to another. Good luck.